All right, everybody, in this video, we want to take a look at an introduction to probability. The idea for probability, it isn't something that's just kind of floating and disconnected from our story. What we want to do is move towards the idea of inferential statistics. And the idea for that is, how does someone know that this presidential candidate has won the state of California at 6 o'clock before all the votes are counted? How do they do that? Or how do they figure out polling for a candidate? How do those things work? Well, in order to understand that, we have to have a better understanding of the ideas of probability. And that's what we're going to start to begin with today. So, okay, so the idea of probability is this. It's you intuitively already know this. It's the likelihood that something is going to occur. So what's the chance that something is going to happen? Now, there's going to be a couple ways we're going to look at this, but before we do, just understand this, that this textbook and many textbooks consider an unlikely event one that has less than a 5% chance of occurring. So you might see that in MyMathLab homework or some other kind of homework. So the way we define this here, this is the probability. Oops, if I could get it to work. There we go. This means the probability, and this inside of here is the event, okay? This means that we are interested in A happening. So if I'm looking for the probability of getting a head on a coin flip, I might write this. Now, an event can be more complicated than just a single item. It could be something like the probability of a 1 or a 2 if I rolled a dice. But this is probability, this is the event, and it equals, so like back here, this is, we're familiar with that being equal to a probability of 0.5. This would be 2 out of 6. I'm happy with either of those. Now, I'll talk more about that in a minute, but what I want you to see is this is probability, this is the event, and you would write the probability after it like that. All right, now a sample space is a collection, as this says, of all the things that could occur. So if you flip a coin, couldn't you get a heads or a tail? That's the sample space. This is everything. Sample space, you could get a head or you could get a tail. It gets a little more complicated, however, if you flip 2 coins. So the first time you could have got a head or a tail, but the second you could get another head or a tail, and you see what's happening here. You could get a head the first time, a head the second, head the first, tail the second, tail the first, head the second, so on. So the sample space, all the things that could occur. So if you were to try to do the sample space and you would roll a dice, be 1, 2, 3, 4, 5, or 6. Make sense? All right, so here's the classical definition, the theoretical definition of probability. It's the number of outcomes, it's the success over the total. Okay, well, the way they're doing this here, this is in the theoretical sense. So if I wanted a heads, there's one way I could be successful at that. There's one outcome that would get me ahead, but there are 2 total possible outcomes. So I get 1 out of 2. Okay, so if I was looking for the probability of getting a 1 or a 2 on the dice, there are 2 possible things that could happen to make me happy. 6 total possible options. So my probability is 1/3. Now this is the theoretical, okay? That's what should happen in a perfect world. Now we can find this here. This is the perfect world. You land on a Y, you get the biggest prize. Find the probability of Y. Well, 1, and there are 8 slices. So there's my theoretical probability. 1 success, 8 total slices. And you could do this on your own. Okay, now what's experimental probability? It's a little different. It's what happened when you did an experiment, when you played a game. It doesn't mean what would happen in the perfect world. It's what happened when you tried this. So, for instance, here's an example. Okay, I don't remember what the story's about. Well, there's 100 people and we played some game. I don't even know what it's about. What's the probability of a 3? Well, we did, how many times did we get 3? Well, we got it 28 out of 100. It's still success over the total, but this isn't the perfect world. This isn't if we had done this a trillion times. It's just what happened in our experiment. Now, how about a 4 or a 5? Well, that would be 11 and 9. I'm happy with either of those. and there were 100. So I could reduce those fractions, and that's the probability. Okay? Now, that's experimental, not the theoretical. But the idea is still the same, success over the total. Now, here's what this slide is saying. The law of large numbers. What it means is if you were to go in a casino and you win the first game you play, the best thing to do is to get the heck out of there. Because in a casino, all the games are stacked against you. That's why they have the game. So the probability of winning a game favors the house. They have a better chance of winning. So you go in there and you win. Well, great, you've won. But what the law of large numbers says is they're not worried, because the more people that play, the outcome is going to go from the experimental, it's going to begin to approach the theoretical. What do I mean by that? So we do an experiment. There's a bunch of people in the casino, but the more and more people that play, the larger the bottom of that probability, the end, the trials, how many people have played, the more people play, this begins to approach that. So this one is stacked in favor of the casino. So the big problem for the casino is they just need as many people to play as they can, because the laws of statistics are saying that it should take them to the theoretical, in which case at the end of the day, they have won more money than you. Okay, so one last idea here that's, well, like two things, I guess. Probability is a long run idea, okay? When we talk about the probability of a coin flip being 1/2, that would be if it happened over and over again. Some experiments, I think it was Pearson actually, the guy who one of the companies is named after, was in a camp in World War II. He flipped a coin 50,000 times. And the more coins he flipped, it doesn't have to be exactly 50-50, but the more he did it, it approaches the theoretical, and it begins to approach exactly half and half. It approaches, not perfect. So probability is established in the long run. If you were to do this many, 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 many times, it doesn't speak to the immediate. So you are not due for an event to occur. So suppose you flipped a coin 5 times and you got heads every single time. You are not due for a tail. It doesn't work that way. We'll talk more about that in the next class. But it isn't due. It's just that it's in the long term. Short term doesn't tell us. If you were to flip the coin 100,000 times, you're going to establish 1/2 or something very close to it. But every time you flip the coin, it doesn't guarantee. You're not due anything. That has to do with random events, which we'll talk again more about next time. All right, so we got some probability rules here before we get a little bit more mathematical. And here are the rules. These are the two I want to focus on at this point. So any event, the probability of anything has to be between 0 and 1. There's no such thing as negative numbers are greater than 1. A probability of 0 means it didn't happen. It's not never going to happen. A probability of 1 means it's guaranteed to happen, or there's somewhere in between. But you can't have a negative probability. There's no such thing. And 1 represents 100% of the time. So any athlete who says that they're giving 110% is not true. There is no 110%. It's at 100. So those are the regions. Now this means that the probability of your sample space has to equal 1. What does that mean? Well, if your sample space is all the things that could occur, heads or a tail, these options have to add up to be the total. There can't be something else that might randomly occur if these are the only options. So if this is 0.5, this is 0.5, they have to total up to 1, or you're living in a different universe, because these are the only choices. Now I'm going to talk about this, I think, on the next slide. Yeah, before I take a look at our first formula for this section, I want you to get the idea between mutually exclusive events. Yeah, well, you know what? Let me do the formula here to help you understand. Okay, so we're going to see that there's what appear to be two different rules for addition. Okay? These look similar. They both say the probability of A or B, but they're not the same formula. What's going on? Well, it's not as complicated as you think, and it's really not, it doesn't require you to memorize two formulas. Let's talk about it for a second. If I were to ask who in this room likes country music, I would ask these people. If I said who likes hip hop, I would ask, and other people would raise their hand. But it's possible that you like both country music and hip hop music. right? Isn't it possible some people raised their hand twice? Well, look at these circles. These are all the people who voted for country. These are all the people who said they like hip hop. These circles overlap. In this center region, which is the people who like country and hip hop, they've been counted twice. Do you see that? Because of the overlap, I counted this part of the circle here. I counted it again here. This region has been counted twice. So if you ever have people that could be in both categories, you have to subtract them once so that we'd have it right. By taking away the overlap one time, we'd have it right. We would have counted this once, and then we would have counted this without doubling over. You see, removing this means we're removing that second time we counted up the center. Okay? Now, that's the general rule. Well, where does this one come in? Well, it's here. Suppose I asked, hey, who was born in the US? Okay? And who was born in Canada? You can't be born in both. You were not born in both the United States. You were not born in the United States and Canada. You can't. So there is no overlap region. There's no center. We never, ever are going to have people who are born in both the US and in Canada. It can't be done. That's called a mutually exclusive event or disjoint. Same thing, just synonyms. It means that they never overlap. Okay, well, if they don't overlap, we don't have that center region, and so we don't have to cut off the duplicate. Okay? So if you want to add up, I'm happy with getting a 1 or a 2 on a dice roll. Well, you can't get a 1 and a 2 at the same time. You can't get both. So I don't have to cut the overlap. I can simply add these. What's the chance of getting the 1? What's the chance of getting the 2? I can add them up because I'm happy with either one. But if I were doing this, I would do the probability of country plus the probability of hip hop. But I'd have to subtract the probability of country and hip hop. Why? Because there are people that might have been both. It is possible here that you like both. But here, wherever that was, this one is not. And likewise, this is not. You cannot roll the dice once and get 1 and a 2. That's impossible. So we can just add them up. All right, I got one final event here, and then I'll show you a little trick on the chart. It's called the complement. The complement of A is everything that's not in A. So what I mean is, if I had the probability of rolling a 1 on a dice, the complement of that is everything else. That would be 2, 3, 4, 5, or 6. And it's a very clever, simple idea, but very clever and quite useful. So the probability of 1, or the complement of 1, is everything other than 1. Does that make sense? And so, if the probability of 1 is 1/6, the probability of everything else is 1 minus 1/6. Because the whole thing has to be 1, so everything else can be found this way. 5, 6. Okay, you tracking with that? The complement is everything else, but you can find it mathematically is find the probability of the one you want. And because the sample set has to total to 1, you could subtract that, and then you'd have the probability of everything else. Let me show you that here. So the probability of 1. Okay, this is experimental. This is not theoretical, but it is 18 over however many are there. I don't know what that is. 30, 66, 67, 68. I think it's 75. Okay, so what's the probability of the complement? Well, that's 1 minus 18 over 75. Okay, which you could find by doing 75 over 75 minus 18 over 75. Okay, does that make sense? All right, that'll get you through.